Um, Hi, everybody. If you don't remember my name, I'm Adam. I'm your TA for MTH 210. So we'll throughout the semester we'll just have a couple tutorials together. It's not weekly. Look at the schedule, but it's pretty much weekly. Um, yeah, so for today, like I was saying, we don't really have that much to do. But I just thought I'd do like another little kind of intro to graph theory kind of thing, but like maybe from with this little program that I tossed together here, just to show you some more examples and blah, 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 and maybe we can play around with graphs a little bit. Yeah. So, and then again, the actual problems for today will take 5 to 10 minutes or something like that. It's not very long. So does anybody want to take a crack at, defining a graph for me? What is a graph? Sure. Sure. That's a good way to, that's one way to think about what a graph is, right? So it's like we're thinking about a binary relation between elements, and it is a way to represent it visually. Now, at the end of the day, when we're using graph theory to maybe like find on Google Maps the shortest path to things, we're probably not thinking about it as a binary relation. We're probably thinking about it as a graph, as its own standalone object. What would the formal definition of a graph be? Yeah.
Well, a collection of nodes that may or may not be related.
Okay, so that's almost there. Yeah, that's getting there. So a graph, maybe may as well write it here, right? So a graph is really formally defined as a vertex set and an edge set. Technically and a relation, but the edge set usually does that itself. So when we're talking simple graphs, the vertex set and edge set. And the vertex set is all the things, and the edge set is all the things that are related, right? Okay, so this is obviously, we've been talking about graphs for a while, so I don't have to maybe talk about that. But one thing we can do is we can draw graphs. Okay, that's the important thing. So here's a little program. So here's our vertex set, right? And then we can connect vertices with edges, right? And so this is an example of a graph of order 3 and of size 2, because it has 3 vertices and 2 edges. And the first really important thing to remember is that graphs are squishy. That's kind of the way I say it. So you can this is all the same graph. None of this actually changes the graph in any way. The graph is the relationship between the nodes. And also, the ordering here, I put some numbers here, but the ordering doesn't exactly really matter, right? So I don't have to number them. I just number them because it's helpful to program it. But the ordering, it can matter in some applications, but in general, we don't care about that. So what's a simple graph? What makes a graph simple? Yeah. Yeah. So it's not exactly about one-way connections, but it is about no loops, right? There's no loops, and then so no loops and there's something else. Double, is that what you're gonna say? Oh, double edges, right? So yeah, so we say there's no multi-edges and there's no self-loops in a simple graph. Okay, so then you can imagine really complex graphs, right? You can imagine that we could have I don't know, you could keep putting nodes here, right? And here I have a magic button that what I'm going to do is I'm going to press this, and all it does is it looks at each edge. Here, how about this? Let me just let me clear it. And then if I just put all these nodes here, right? And this makes what's called a random graph, GN12, GN1/2. So it just looks at every possible edge and it tosses a coin 50-50 if it puts an edge there. So that's what we get. Oh, is it not going to? Oh, is it? Okay, it might be crashing on me. This is what happens when you make your own program here. Okay, let me just restart it. Pause your amazement. 1 second. Yeah. So let me try that again. Maybe it doesn't like it if I do the GN1/2 twice. So let me just put a couple more nodes, whatever, and then GN1/2. Okay, I guess it worked once, and now it doesn't want to work second time. So that's annoying. Is it gonna crash on me? Yeah, it is. And I close everything. Okay, give me 1 second. Anyways, so my point is mostly that using this, we kind of show what graph isomorphisms are. So that's the word that he was kind of tossing around there in the lecture a little bit, right? So we would say that this graph here. How about this? So if I have if I have K, why it's not letting me do it? So if I have the complete graph, why is it worked a minute ago? I'm sorry, I don't know, this is annoying. Okay, I'll just not press any of those buttons anymore, and I'll just do it myself. That's so annoying, because I swear everything was working perfectly this morning, and I have no idea why it's not. If I have K4, what does K4 look like? What does that mean when I say if I have K4? Yes. And there's 4 nodes, right? Yeah. So this is K4, right? And then he said that there's another way to draw K4, and it's the same thing, right? So that's the idea, is like if you take any of these nodes, I deleted it. If you take any of these nodes and you shift it in, right? So now this graph is the same as K4. Nothing changed structurally, right? The graph is all about the structure of the edges and the nodes and everything like that. But this is just another drawing of it. And so we'd say that this graph and this graph are isomorphic. Okay, so an isomorphism is basically just like a really fancy way of saying it's just kind of relabeling. That's all we've really done. Okay, so it's like, you know, this graph 1, 2, 3, 4 is the same as this graph 1, 2, 3, 4. We've kind of just moved things around, right? So the 4 in this goes to the 4 in this, and that's all that really is different. But the edges and non-edges are preserved between the two. Yeah.
So there are some characteristics that are obviously like not changed that are like part of the structure.
Yeah.
Of the graph, but we also talked at one point about edges that cross.
Yeah, like a crossing number, right?
Yeah.
Yeah.
Are there any other characteristics of graphs that can change with different drawings that are?
Sure. Anything geometric. Anytime you put the geometry of it. So anytime you think about like, oh, what's the angle between these two edges and things like this, right? So that would be like a geometric property of the graph, which we most of the time don't care about, because the graph itself is more about the structural property. What's related to what? What's related to what? It's like with a binary relation, we just really care what's related to what, not like what are the angles between the two binary relations, unless maybe there's some reason we care about that. And then you start talking about geometric graph theory, okay? And then you have some things like that. But one important property is the crossing number. So that is something that's kind of relevant. So like here you can draw this with no crossing, right? There's no edge crossing here. So we'd call this a planar graph, okay? But other graphs, like you just can't do that, right? So I don't know what, like the Peterson graph, he loves that one. But also, I think K5 is almost certain it's not planar, right? So if I have K5 like this, where does that have to go? There, and then that has to go there, and there's K5. I mean, I don't know, I'm not proving it to you, but like we can kind of shuffle around the edges here, and we can try to see, you know, is there a way to draw it without any edge crossing? I feel like no, you know, like looking at this, right? Like there's an edge crossing there, but so I guess maybe this 8 and the 7, there's always going to be an edge crossing between either 8 and 7 or 8 and 9, right? So like K5 seems like it is not a planar graph. And so when I refer to a graph, when I say K5, technically I really mean any of the isomorphisms of K5, any of the rearrangements, any of the kind of, you know, the graphs are squishy, so you can kind of squish it around and kind of decide any one you want. So that's important. So that's one thing that I like about showing it like this, because then you remember that they can move, right? So it's like if I have a path, then this is a path, but like this is also a path, right? That's the same. There's nothing different about that graph than the one I had before. Okay, and then we just have like some specific graphs. Okay, can I clear it? Is it going to let me? I hope so. Okay, so far so good. So if I have like, if I want like, okay, so path is already mentioned, right? We can also have like a cycle. Cycle is also pretty obvious. Let's see. Okay, it worked. Cycle worked. So we can have like a cycle of any length, right? And we're always talking about finite graphs here, right? What does that mean when I say that? We're talking about finite graphs. Not infinite. Infinite what way?
Count the number of nodes.
Yeah, you can count the number of nodes, exactly, right? But even like technically that's not enough because you can count all the natural numbers, right? But they're still infinite. But they are finite, so you could you can count all of them in a finite amount of time. I guess is the thing. Yeah, so basically the vertex set is finite. If the vertex set is finite, then the edge set is of course finite, right? If I have n nodes, what is the maximum possible amount of edges I can have?
N plus 1.
Not quite 2n, not quite n minus 1. If I have n nodes, I'll get to you in 1 second. If I have n nodes,
N squared minus N over 2.
n squared minus n over 2. Yes, that is what it is. Why?
Combination.
Yeah, right? So it's like n choose 2. Right? So I don't know if you did choose, like have you talked about like the C and CR? Yeah. So it's like how many subsets of size 2 I can make from n. So n choose 2 is the number, which is n times n minus 1 over 2. Yeah. Did you have a question or something you wanted to?
Yeah, it was about the crossing number.
Yeah, tell me the question.
I was just wondering if the crossing number is specific to different drawings of a graph, or if a graph, if it's just like the minimum.
Well, I think, yeah, that's a good question. Well, we can just look at how it's defined. I don't, let's see. So, crossing number of a graph, right? So let's take a look at, so in graph theory, the crossing number, CRG, is the lowest number of edge crossings of a plane drawing of the graph. So plane drawing meaning on a piece of paper, right? And is the lowest number. So if I say, what's the crossing number of this graph? I'm looking at all the isomorphisms, all the different drawings of it, and I'm finding which was the smallest number. Right? To be honest, I haven't actually personally really studied crossing number that much, but I know a little bit about it. And the main thing is, like, if you can draw a graph, if there is an isomorphism of the graph that has no crossings, then it is a planar graph. And planar graphs are actually really interesting. Like, they have a lot of applications in like AI and things like this, and big words. So obviously as math people, we're more interested in the theory of it, but this is a math and applications program, right? So there's lots of applications of this stuff. Yeah, so anyways, that's that. I wish this worked. Can I put a couple more nodes and see if it'll work? And if it doesn't, if it crashes, boom. Hey, it worked that time. Okay. So that's like, I guess something I could talk about a little bit too is one really huge thing that we talk a lot about in graph theory is random graphs. So random graphs are graphs that you construct through some random process. So this is the one that I'm giving you as an example, right? So it's like I gave the computer 8 nodes, I guess, right? And I said, for each potential edge, just flip a coin 50-50, will there be an actual edge there in the actual graph, right? And sorry, it's hard to right click on a trackpad. There we go. So random graphs have a lot of really good applications in we call like modeling. I'm kind of talking a lot here, but just giving you some ideas, a bunch of different places that graph theory is relevant. So you can imagine, like, in real life applications, we talk about huge graphs, right? We talk about like the web graph. The web graph is the graph of all the websites, and each node is a website, and they're linked together if there's like a link between the pages, right? So if you're like, I don't know, on Google and then you click a link, it goes there, but it also counts if you're like on someone's YouTube page and you click their video, that's like a link. So you can imagine this is like, huge. This is a giant graph. And we want to study it, but we can't, no one has that saved on their computer, right? No one has that saved on their computer. So instead, we'd really like if we could kind of simulate it. Is there some way to simulate it in an accurate way? And so random graphs are a really nice way of doing that because we can control the size of it. We can say, I want a simulation of the web graph, but I only want it to be 10,000 nodes, not a trillion nodes, and then I can study properties of it, and I can and to know if my simulator is doing well, I need to compare it to the actual web graph in some way, and so we do a lot of that's pretty data sciencey. Yeah. Anyway, that's that. So that's something I study a bit. Anything else? Anything else that I can show you in this? Well, it might crash. So, bipartite. I can show you bipartite graphs. So let's see. Clear? No. I think if I click something 3 times in the menu, that's when it says it's had enough. So I'm gonna not do that anymore. Hopefully it works. I swear this morning, maybe I didn't test it enough. Maybe that's what it is. Anyway, so a bipartite graph is a graph that can be two-colored, right? Come on. So like okay, C5, right? So if I have C5, right, then I have this. Is it C5? Yeah, it's C5, right? Not C6. Boom. No, it is C6. Right, because yeah, C6. So this is C6, cycle of 6 nodes, right? And it can be two-colored. And what that means is that I can assign, using 2 colors, a proper coloring. And that means that every edge has a different color. So if I start with purple on 1, then I have my orange on 2, purple on 3, orange on 4, purple on 5, orange on 6, right? And so then this is a bipartite graph. Because every edge has 1 color on each side. Bipartite graphs are usually drawn differently. Bipartite graphs are usually drawn kind of like this. Or at least they can be, they're isomorphic to something like this. It's really hard to right-click on a trackpad. There we go. That is what a bipartite graph is usually drawn as. This is still C6, right? This is still a cycle with 6 nodes. But now it's drawn kind of as these 2 independent sets, right? So 2, 4, and 6 form what's called an independent set because none of them are connected. And 1, 3, 5 also form an independent set because they're pairwise not connected. No pair of them are connected. And this has a lot of applications in like one simple example is like a matching, stable matching. So it's like if you imagine these are like people and these are jobs, then a company might want to assign their 3 workers to 3 jobs in some way. Right? This is a complete, this is a complete bipartite graph between every edge that's possible there is there. But you could just assign 1 edge, or you can assign 1 person to 2 jobs. But you never assign a job to a job. That doesn't make any sense. You never assign a person to a person. It's like matching between the 2.
Sorry, so this is a complete bipartite set?
This is a complete bipartite graph.
So one is not connected to 4.
It's not a complete graph, but it is a complete bipartite graph, right? Which means that every possible edge between the 2 sets are there. If I connected 1 to 4, it's not bipartite.
Why not?
Why isn't it bipartite?
Why isn't it bipartite?
If you connect 1 to 4.
Oh yeah, you're right. That's right. I was counting it wrong. If I click this now, let's see if my button works. No, you're right. If I click, there you go. That's the complete bipartite graph.
Yeah.
Good. Yeah, thank you for checking that. That's correct. This is the complete bipartite. So what I had before was just maybe a matching, right? It could be like saying like assign this to this person to 6 jobs or whatever. So yeah, sorry. So C6 is bipartite, but it is not the same isomorphic to the complete bipartite graph.
So if there's only connections between like sets like 3 and 2 are connected, 2 and 4 are connected, and 5 and 6 are connected, and there's no other edges, is there a specific name for that, or is it just?
It's still bipartite. It's still bipartite. Like you're saying, there's only 3 edges.
Yeah, like rather than a complete.
It's just bipartite. It's just bipartite.
Is it?
Right? It would also be like disconnected or whatever, right? So yeah, but yeah, like if you just had these edges, like this, and this, then yes, that is a bipartite graph. Because you can just color each side of each edge 1 color, right? And then you get 2 sides. But again, it's less about the colors and it's more to do with like the colors can represent assigning the nodes to like a class where it doesn't make sense to like assign someone to someone with the same class. It's like when you're matching jobs and people, you want to match a worker with a job. You don't want to match a job with a job or a worker with a worker. So that's the point of bipartite graphs. You can have like tripartite graphs, if you want to call it that, right? Where it's like you have 3 classes. So it's like you want to make a 3 coloring. And so that means you have, I don't know, jobs, workers, and I don't know, HR reps or something like that, right? So you want to make you want to assign, it doesn't make sense to internally assign anything, but it does make sense to kind of assign pairwise between the sets. Yeah, so the complete bipartite graph is just where every possible edge between the partite sets is. Yes?
Say you took away every single edge, it's still bipartite.
Yeah, sure. Because anytime you have for all blank, and then that blank has nothing, it's true. So if there's no edges and your condition is for all edges, you can color one side one color and the other side the other color. Then yeah, if there's no edges, then sure, yeah, you can do that because there's no edges, right? Yeah.
So, because you said that there's like tripartite and stuff like
Yeah.
that, is chromatic number?
Yeah, it is basically the chromatics. It's basically the same thing, right? Because if I'm yeah, it's basically the same thing, but it wouldn't be complete, I guess. But yeah, it's basically the same thing because if it's three colorable, that means you can assign using three colors. You can assign each node a color where no edge has the same color on either side. So that's the same thing as having three partite sets, and there's no self loop within any of the sets. There's no red to red or blue to blue or green to green or something like that, right? So yes, they're the same thing. The chromatic number is like the smallest possible number of colors you can use. It's always like the smallest, right? The maximum number. What's the maximum number? What's the biggest number of colors you could use to color a graph? What's the maximum number of partite sets you can have? Yeah. Number of nodes. Number of nodes. In this case, 6. So most of the time, all these things are bounded by the number of nodes. But that's a pretty bad bound, right? So it's like the cop number of a graph, which is what we talked about before in the previous lecture, right? Which is like the number of cops you need. Well, if you had 6 cops, then you could just put a cop on everything. So you're always trying to find the smallest. And it's usually related to some sort of, well, you want it to be related to some kind of structural property. Where it's like, I look at this, and I say, well, is there some way for me to just tell by looking at it that this is cop wind? Okay, that's kind of the thing we're interested in. And there certainly is. Cop wind meaning like one cop is enough. One thing I want to share quickly. Well, anyways, maybe I'll get to that in a second. Any questions about this stuff? Bipartiteness or, yeah.
I'm sorry, I'm stupid. How does one cop is enough?
Well, I'm not claiming there's one cop for this one. I don't know. Maybe it is. I just like. So to tell if one cop is enough, you check if there's like corners, right? So like this node, yeah, there is.
Okay, yeah, no, sorry. I thought you said one cop was enough for this.
I think it must be 2. Bipartite sets, bipartite graphs. But it's reflexive. Yeah, I don't think 1 is enough. No. Yeah, it's not enough. Of course, it's not enough.
No, I was going to keep escaping from the other ones. Just think of it as a Z formation.
Yeah.
It goes up, it goes down.
I couldn't list you the exact theorem that tells us that this is 2 cops, but just the fact that I don't think I see any corner. Right. The corner is like this node can see these 3 nodes. But even if there's a robber, so if the cop's here, if the robber is here, you can always escape back to the other side. There's never a connection.
No, I just thought you said 1.
Yeah. No, I get it. And now I'm just thinking out loud. So I think it's 2. Anyways, yeah, cops and robbers are very, very, very fun thing to play on graphs, right? You don't think that maybe it's so important. It kind of seems like just a game, but it there's a whole book. I showed some people before this, right? It's a whole, our professor wrote a whole book on it. So far making sense? Hopefully it's kind of interesting, me just kind of sharing some graph stuff, right? Graphs are very cool. Question? I could talk about a homework problem if you want to talk about a homework problem.
One of the problems were asking you to find the diameter.
Yeah.
And I don't recall that.
What that means? Yeah, for sure. So the diameter of a graph. Okay, let's see. Is it gonna be annoying? Can I still? Okay. So the definition of the diameter of a graph. So just like if we think about it, right? It's if you imagine a graph as kind of like a blob, which is obviously which is usually how we graph just an abstract graph. How we plot an abstract graph is just like a blob, some interconnection of nodes and edges. Then the diameter is like what is the maximum kind of like way I can, if I made it into a circle, what's kind of the maximum kind of middle distance there? So that's a very, very not very rigorous definition there. The main idea is like it's the longest, shortest path. So if I have 2 nodes that are 10 hops apart, and that is the longest, shortest path between the 2, then there's no way for me to kind of, if you imagine the edges being kind of like toothpicks, so they can't squish, then that's kind of as small as I can make it, right? Because that's the longest, shortest path. I could have shorter paths, but that's fine. That can kind of squish together. So That's a lot of talking. Is there a specific graph? Is that the one? So let me just plot it quickly. So is it going to clear for me? Okay, hopefully it doesn't freak out on me. Okay, so A to B to C, D, E, F, G, H.
Also, it does say in the textbook, so like I've run into questions where
Yeah.
like Dr. Bonanno hasn't mentioned thing in class, but there is like a definition
In the question or something
it
like
would be
that.
hard to find, but,
Yeah, right. Can I still see this? Let me see. Is that it? Did I get it right? No, I'm missing one edge. I'm missing this to this. Is that it? Yeah, that's it, I think, right?
Yeah.
Okay, so here's our graph. We want to find the diameter, right? And so just to, just to write it down, right? Diameter of a graph, just so you see the actual definition. Is the greatest well, we don't have the AI overview. Maximum distance between the pair of vertices. And the distance is the shortest path. That's how we measure the distance, right? Let's look at the Wikipedia thing. It's probably better. Is the furthest distance, well, they mean, by distance they mean, yeah, for the shortest path, distance in the graph is the diameter of a set of vertices and for the shortest path distance. So we look at all the paths, right, between these vertices, and we just try to find what are the two vertices that are like the furthest distance apart, right? So yeah, like looking at it, right, so it's like if I just start comparing, right, so like from 1 to 2 is 1, 1 to 3 is 2, it's a distance of 2, right, 2 hops then you do. 1 to 5 is 3 hops. I could also do 1, 2, 3, 4, but that's not the shortest distance, right? There is a shorter path. So to find the diameter, you consider what is the longest, shortest path. And that might be from 1 to 7. 1, 2, 3, 4, 5. I don't think there's a shorter way to do that, right? So 1 to 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Well, but it's longer, so it doesn't count, right? So it seems like this kind of path here is the problem, right? So if again, like, it'd be nice to have like an animation here or something like that. But if you imagine the edges being kind of like toothpicks, so what I mean by that is like they can turn, but they can't squish. Then if I were to try to make this into a circle, then that would be my problem path. That would be the thing that makes the circle big, right? Because I can't squish that kind of. I can fold it maybe, but I can't like squish it together. So that's like my longest. So that's like the diameter of the graph. Does that match the answer in the book? I hope so. Yeah? Okay. Yeah. Yeah. What was it? Sorry? Oh, 1, 2, 8, 5. Yeah. Yeah, it is the same. As long as the distance is the same. It doesn't have to be unique, right? But
the answer just says A to G, but it's the same.
yeah. As long as it's length 5, right? The diameter is 5. Because sure, there are shortest paths, like from 5 to 8, that's 1. But we're looking for the longest shortest path, which in this case is from 1 to 7, which is the length 5. Yeah.
So like to kind of rephrase the definition for all your vertices, they all have shortest paths between them.
Yeah.
Kind of the longest of all those shortest.
Yeah.
paths between all the
Exactly.
vertices.
Exactly. That's right. So I'll just repeat that, right? So it's like you imagine like every pairwise distance. Take a list of your vertices and an identical list of your vertices, and you can imagine all the different distances between all the nodes, right? So from 1 to 1, it's less than 0. From 1 to 2, it's 1. From 1 to 3, it's 2. And then you just, out of that list, you consider the longest one, and that is the diameter of the graph. And it sounds kind of geometric, right? It sounds kind of like we're talking geometry. So that's why I'm giving you this analogy of like squishing a circle, just trying to morph it into a circle. But it's really not geometric. It's really just structural property of the graph, the longest, shortest path. Yeah.
So, if there are two nodes that don't have a path between them,
Then the diameter would be infinite, right? So we'd say that the longest, shortest path is infinity. in that sense, we usually like to just talk about like the diameter of a connected graph, right? Because the diameter, or if it's disconnected, then we would just say what is the diameter of the components of each component, right? Connected. Yeah. Yeah. Well, it doesn't really make too much of a difference. So you're always saying like loop from 8 to 8, like Phelps loops.
That'll be
Well, no, like with the distance from 8 to 8, loop or not, is 0. If there was a loop, then still the distance, which is the shortest path, is 0. If there's a loop, you could say there's also a path with length 1, go along that loop. But that's not the shortest path. If you're at 8, the distance to 8 is 0.
this is just one node and loop and so.
Yeah. So then let's.
That sounds like that.
That'll be one.
The longest, shortest path is 0. Because what's the shortest path from that node, let's say node 1? From node 1, well, A. Node A to A. What's the shortest path?
0.
Well, just stay there, 0. Technically, there is also a path of length 1, but we want the shortest path, right? So it's 0. Good, does that answer your question? Is that okay? Any other comments, any questions, anything you want to think about? Yeah, okay, so let's maybe talk, again, the questions will really just take a few minutes. So let's maybe talk a little bit about subgraphs a little bit. We can talk about like induced subgraphs versus subgraphs and things like this. I know that might have been a little bit confusing in the lecture about what the difference between those two things are. So let's clear this. Fingers crossed that everything's okay. And then let's take a look at this. So I will connect maybe the nodes like this. Okay, so let me just make sure this is a good example. So yeah, so an induced subgraph, which is what we're going to talk about first, is me saying, let me take I'm just going to pick out some nodes. And I want to just kind of keep the edges those nodes, first of all, and I want to also keep the edges that are related to any of those nodes. So remember, subgraph is a part of the graph that is still a graph. Okay, so it's a sub part of it. That is still a graph though, right? So I could say like just this edge is a sub part of the graph, but it's not a subgraph. It needs vertices, and the edges need to be connected to vertices. It still needs to be a graph. So if I just select these nodes, right? If I say, okay, I want to induce a subgraph by looking at just 1, 2, and 3, then the result I would get is just a triangle. Does that make sense? I'd basically be losing out on these edges and that node. And so remember I said the definition of an induced subgraph is we just select some vertices and we say I want to keep all the edges that are related to those vertices. So by that definition, maybe I should keep this edge. But if I kept this edge, it wouldn't be a graph anymore because I have an edge that leads to nowhere because that's being chopped off. I've unselected that node there. So you get rid of all those superfluous edges, right? The ones that kind of aren't connected to anything, those automatically just kind of get